So this is find the inverse of each function. Again, this is, I think, the back of the third page of your review for a semester exam. So inverse functions. We talked about inverse functions with all of the functions we worked with this semester. Quadratic's inverse was square root. Okay, so square root and quadratic are inverse functions of each other. Log and exponential are inverses of each other. Cube and cube root are inverses. Okay, so all of those different pairs we worked with, and we just talked about the basic concept of what an inverse is. So an inverse is when you switch x and y. Okay, so if you're trying to find the equation of the inverse, you're going to switch the x and y and solve for y. Okay, now if yours is written in function notation, meaning it has f of x, you'll have to understand that f of x is the same thing as y. So I'm going to switch where the f of x is and make that x, and where the x is, make that y. Now I want to solve for y. Okay, so I'm going to just do basic algebra here. I can't combine a variable and constant, so it's just x minus 5. And then I have to divide out the coefficient of 2. What you do to one side, you do to the other. The entire other side gets divided by 2. So when we go to write this, remember we write inverse with that little -1 power to indicate that this is, the original was f of x. This is the inverse of f of x, or f inverse of x. Okay, so the inverse of 2x plus 5 would be x minus 5 over 2. Now you could individually divide those by 2, so that could be 1/2 x minus 5/2 if you wanted to separate it, okay, but that means the same thing. Now, graphically, inverses are reflections across the line y equals x. So a way that you could do this using Desmos on a multiple choice test is you could type in your original function, okay, and you could see that line. This is a linear function, okay? And then your answer choices, you could type in one answer choice at a time to compare. Now, they are not supposed to be the same graph. They are inverses. They are supposed to reflect across the line y equals x. Okay, so I'm going to make that line red and dashed. Okay, but that line y equals x, that's what the graph is supposed to reflect across for an inverse. So if I type in this inverse that we came up with, which is x minus 5 over 2, and then you can see, if I were to fold it along that dashed line there, wouldn't that all match up? Don't they intersect on that line? Okay, so if you're more visual for inverses, you can look at this graphically. You can just plug in the original function. Okay, I would definitely put in the line y equals x as a visual help. Okay, and then put in your answer choice A and see if it's a reflection across that dashed line. If it's not, put in answer choice B, C, D, and just find which one is a reflection across that line. So graphically, inverses are a reflection across the line y equals x, okay? Or you can do them algebraically like this, okay? So you have some options on ways to find inverse functions. So for B, I'm going to switch my x and y. Now, to solve for y here, I've got to get rid of that radical, that square root. What's the opposite of taking the square root? Squaring. So to solve this for y, I'm going to square both sides to start. That's going to get rid of the radical. So then I've got x squared equals 2y plus 4, and I'll subtract that 4 over. So now I've got x squared minus 4 equals 2y, and then I'll divide that 2 over. And again, you divide the entire other side. So I'm going to write that as f inverse of x is x squared minus 4 over 2. Okay, and you could check that graphically and make sure that if you typed in this function and you typed in this function, that they are reflections of each other across the line y equals x. Okay, C is an exponential. So when I switch that, I will have x equals 2 to the power of y. So when we did exponentials, we said their inverse was logs. Pause real fast before I continue this problem. Just knowing what types of functions are inverses may help you eliminate options in a multiple choice test. So knowing that a linear's inverse is still going to be linear, okay, or knowing that a square root's inverse is going to be quadratic, or a quadratic's inverse is going to be square root, or an exponential's inverse is going to be a log. Those things can help you eliminate answer choices that aren't even the right type of function. Okay, so keep that in mind. Okay, so to solve for y, when y is in the exponent, we need to rewrite this in log form. Okay, so I'm going to refresh. Okay, when we have an exponential, what is the base of the exponential becomes the base of the log. So this is a log base 2. Okay, and then what the exponential equaled is the argument of the log. That's what we're taking the log of. And then what was the exponent is what the log expression equals. So now I've solved for y by rewriting it from exponential to log form. Okay, now I want to make sure I indicate that that's the inverse of y. And that's not y, that's the inverse of y. Because y was 2 to the power of x. So the inverse of y is log base 2 of x. You feel okay with that? So those are inverse functions of each other. Okay, and you could have easily eliminated knowing that that is an exponential equation. If you had any answer choices for inverses that were not logs, you could have knocked those out, known those are not right. Okay, so same thing for D. This is an exponential, so I know the inverse is going to be a log. Okay, but I'm going to switch that x and y. And then I'm going to solve for y. Now, before I rewrite this in log form, I have to isolate the exponential expression, so the 3 to the y. So I need to add that 1 over to the other side. So I have x plus 1 equals 3 to the y. So now I can rewrite that in log form. So the base is a 3, so this is going to be log base 3. Okay, and then the argument is x plus 1. So that's what we're taking the log of. And then the exponent is the y. And that I've isolated the y, and so I'm going to indicate that that's the inverse. Now I'm going to go ahead and do f while we're talking about logs and exponentials. So this one starts as a log. Okay, we're going to take x and y and switch them to find the inverse. So this is a log base 4 of y now. Now to solve for y, right now it's in the argument of the log. I need to get it out. So I'm going to rewrite this as an exponential. So I'm going in reverse of what I just did. So the base of the log becomes the base of the exponential. Okay, what the log equals is the power, so that's x. And the argument of the log is what that is equal to. And that's the inverse equation here. So you've got to be able to convert back and forth between log and exponential to be able to do those inverses for exponential or log functions. All right, last one over here, E. I'm going to switch the x and y. And then I want to solve for y. So first, I'm going to get rid of that denominator of 4 by multiplying it over. So I've got 4x equals y minus 2. Now I'm going to add that 2 over. I cannot combine that 4 and 2. That 4 is the coefficient of the variable term. The 2 is a constant. So it stays as 4x plus 2. Okay, and I indicate that it's the inverse with that little -1. Oh, and actually that one was in function notation. It said f of x. So I'm going to write that in function notation. So f inverse of x. Then whether I use inverse of y or f inverse of x, I just look at what it was originally given as y equals or f of x equals, and I keep it consistent. Okay, now again, all of those you could have done graphically. to see the original graph and then type in the answer choices and see which one is a reflection across the line y equals x. Okay. So as long as you understand graphically what inverses look like, that they reflect across the line y equals x, you can work them backward from the answer choices that way in Desmos. All right, now these say verify that these are inverses by graphing. Okay, so that's what I was just saying. To verify that these are inverses, that when I graph both of them, they should be a reflection across this line, bless you, y equals x. I'm gonna go ahead and draw that line, y equals x. Yeah, there's only two of those. Okay, now it's asking me to graph them. I can graph these by hand. I know my transformation rules and I know what my cubic parent function looks like, and I could graph this by hand, plot points, make a table, however I want to do it. But I don't have to. I get Desmos the entire test, so I may as well use it to help me graph. So I'm going to graph this x minus 1 cubed minus 1. Okay, so this is the first function, the original function. Okay, and I can zoom in here and I can click on some points to get them. So it looks like that point of inflection here is at 1, -1. So I'll plot this in one color. So at 1, -1. And then there's a point at 2, 0, and 0, -2. Okay, and then if there's any others that might fit on our graph, looks like 3, 7. That's not quite going to fit on our graph. If you want to estimate it, you can, or you can go ahead and just draw this the best you can. Be up here. Okay, so that's the original f of x. Okay, now we want to graph the second one. G of x is the cube root. Now you'd have to be able to use Desmos. To get a cube root, any root other than a square root, you have to go to functions and scroll down. I think it's at the very bottom. Yeah, this nth root. Okay, and you can type in whatever root you want. So we want the cube root here of x plus 1 and then plus 1. Okay, so that showed up in blue. So let me get blue this time. And I can see that the point of inflection here is at -1, 1. So I'll start there. Okay, and there's a point at 0, 2 and -2, 0. And I can graph that curve. Now, visually, does that look like it is a reflection? These two lines are reflections of each other, or curves, I should say, not lines. That these two curves are reflections of each other across this dashed line? If I were to fold it across this dashed line, would all those points match up? And you can even confirm with the actual ordered pairs. Remember, your ordered pairs should, the x and y should switch. So if this blue one has a point at -2, 0, this one should have a point at 0, -2. This one has a point at 0, 2, so this one should have a point at 2, 0, because the x and y switch. Do y'all see that? Now again, if you want to put the line y equals x there as a visual, you can, and you can make it dashed in whatever color you want, but there it is, or dotted, dashed, okay? Can make it a little thinner. It's just barely there. Okay, so these are a reflection of each other across that line. So yes, if they reflect across that line, that confirms they are indeed inverses. Okay, let's try that over here. So if I were to graph, this one is 3 times x cubed minus 1, and then 1/3 times the cube root of x plus 1. All right, so taking a look at those, do you see how they're slightly off from that line? These don't look like they would overlap perfectly when I folded on that line, y equals x, do they? Do y'all agree or disagree? Okay, and you could even check points. So on this blue one, there's a point at 0, 1. So on the other one, there should be a point at 1, 0, but there's not. The intercept's at 0.6930 instead of 1, 0. So I can confirm by looking at these graphs that they are not inverses. So I guess I should have written, yes, these are inverses. Okay, no, these are not inverses. Okay, and when I graphically look at these, I'll get some points. There's a point we said at 0, 1. Okay, and then it's hard to see these other points. Maybe, so this is at -5, like 0.4. Like here. And at +5, about 1.6. About here. So I can kind of get the general shape of this curve. Okay, and then for the red one, there's a point at 0, -1. And then that x-intercept's at about 0.7. Then there's a point it's about -1.1, -5. About down here. So notice the point where they intersect is not on the line y equals x. So these are not inverses. The points are not x and y switched. So these are not inverses. So you know what to look for if they are inverses. Notice the intersection is on the line y equals x, and they reflect across that line. Okay, like these points were at 0, 2, and this one was at 2, 0. Okay, things like that to check for. You feel okay about inverses? All right, and these were done with cube and cube root, but this is true for any type of function. If they are inverses, they should be reflected across that line, y equals x. Oh, a couple more. So we're confirming or denying if these are inverses. So I'm just going to pull up the graph. I'm not going to actually take the time to graph these on the paper. We'll just check them graphically. Okay, so this first one is 1/3 x squared. Finish. Thank you.
So this one,
Hang on, I'm in the middle of recording, so show me later, okay?
all right.
All right, okay. Or you can show me in tutorials. All right, 1/3 x squared is one of the functions, and the cube root of 3x is the other one. So I got to go back to here and get the cube root. And it was of 3x. Oh, I'm sorry. That's the square root. I don't know why I'm thinking this is the cube root. I made that more complicated than it needed to be. Square root of 3x. All right, so we've got the square root of 3x and 1/3 times x squared. Okay, and then there's our line. Now, with quadratics, it's a little tricky. There are those excluded values, okay, for quadratic and square root as inverses, because a square root function is only half a parabola, like on its side, okay? So this half of the parabola on the right side is the inverse of this square root function. Okay, do you see that? Now, so yes, these are inverses, but we need to put the excluded value for the square root. We need to say where x is greater than or equal to 0. Okay, because we only want the right side from here, from that 0, 0, from where x is 0 and greater than. So everything to the right of that, only that portion of that parabola is what is the inverse. Okay, so I guess I will show that one on the paper because that one's slightly different. Okay, so 1/3. So plug in a 3 squared is 9 divided by 3 is 3. So you can confirm those points on here. There should have been a point at, 3, 3. So that's just the right side. You have to have that exclusion. Okay, and then when you graph this one, it's the square root goes through those same points, but like this. So yes, they're inverses if you restrict this one. If it's not restricted, then they're not inverses. They're only going to be inverses if you put the restriction. Okay. All right, then on D, see, we've got x squared plus 2 over 7. And we've got the square root of 7x minus 2. So same concept here, because we have a quadratic again, which is a full parabola, and a square root function again, which is a half parabola on its side. Okay, so we would have to restrict the square root function again, or excuse me, the parabola, the quadratic again, and that is from here where they intersect. So this 0.298 is where the this one starts. Graph that. All right, so that one's in blue, where x is greater than or equal. Okay, it's restricted to that 0.298. If they don't have the restriction listed, then we would say no. And then that one is in red. Okay. Oh, this is what we were just talking about. The line of the original function and the inverse reflect across the line y equals x. Always, y equals x. All right, so now we're getting in here in the next page. We're getting into exponential and log functions. Now again, here is that rewriting between log form and exponential form. We used that a minute ago when we were doing the inverses, but here it's listed out again. Now they're asking us to solve. Okay, so solve each equation. Okay, so we want to solve for x. We're going to want to get x out of the exponent in these exponential ones. There's a few options that we learned. If you think back, logs were unit 11 and exponentials were unit 10. So if you need to go back and look at any of your notes, unit 10 is exponentials, unit 11 is logs. Okay, but we talked about one-to-one property. We talked about rewriting from log to exponential form. So those are some of the strategies we'll use here in the review as well. All right, so for A, I'm trying to solve this for X. One way to do this is probably the easiest way, since you get Desmos, the easiest way to do this is just to rewrite it in log form. Because I know that if this is the base, if I was doing it algebraically, this is not the way I would do it. But the fact that you get a calculator, this is the way I would do it. So the base is 1/3. So I'm going to do log base 1/3 of 27 equals x. And then you can simply type that in Desmos. To type logs in Desmos with a base, you can type log, L-O-G, but that's only for common logs, or if there is, that's when no base is written, it's an understood base 10. Okay, if you need a base, you got to scroll down here. I think it's under the calculus section. Maybe I passed it. Yeah, here it is. So log with a base value, and you can type whatever base value you want. So we said 1/3. So log base 1/3 of 27, boom, -3. That's your answer. Now, again, if you were having to solve this by hand, that's not how we would do it, but you get Desmos, so that's probably the easiest way to do it is just convert it and plug it in the calculator. Convert it from exponential to log and type it in the calculator. Now in B, you have x in 2 places, so you can't do that. What we can do is do one-to-one property. If we can get these bases to match, then we know that the exponents must be equal to each other. Okay, and I know that I can rewrite 25 as 5 squared. So the left side just stays as 5 to the 3x, but instead of 25, I'm going to write 5 squared. So I'm replacing 25 with 5 squared, and then it's still to the x minus 1. So the fact that I got that one-to-one property, now I've got a power to a power. When you have power to a power, you multiply. So here we have to distribute that. And we got our bases to match. So that means we can essentially just drop the bases and look at the exponents. So that's just going to be 3x equals 2x minus 2. And then I'm going to solve for x. So I'm going to get my x's to one side. So I'm going to move the 2x over by subtraction, which is going to leave me with just x equals -2. All right, C is similar to A, where x is only in one spot. So the easiest thing for you to do, since you have access to Desmos, is just to rewrite this as a log. So the base is 4. So log base 4 of 0.25 is X, and just plug that in the calculator. So let's see what log base 4 of 0.25 is. It's -1. So use Desmos. So for A and C, I just used Desmos. I rewrote it using this rule, and then I plugged it in Desmos. I can do the same thing for D, E. F will be a little different. So let's go ahead and do D and E, that same method. So the base is 10, so this is going to be log base 10 of 15. I got to just type that in the calculator. This is a base E. What happens when you have a base E? What's a log base E? A natural log, so ln. Because log base E is just natural log of 24 equals 3x. Now, this one does have an extra step because it's not just equal to x, it's equal to 3x. How are you going to get rid of that 3? If you have 3x and you want to get rid of the 3, what do you do? So I'm going to divide that 3 over. So that's what I'm going to type in the calculator. Natural log of 24 divided by 3. So I'm going to pull up my calculator. So over here, it's log base 10. And I actually don't have to write log base 10. And do what I just did there. If you just do log, that is a base 10. So if you write no base, that's a base 10. So just log of 15, and that's my answer. Okay. You are going to have a multiple choice test. So your multiple choice questions are probably not going to be written in this format with an irrational decimal like this. They would probably be written as a fraction if possible. But otherwise, that's it. Log base 10 of 15 is this. Okay, so we'll just round it. And then if your answer choices were not decimals, you just type them in and get them as decimals to see which one matches. Okay, so X is approximately, and I'm going to say approximately because we're going to have to round that, 1.18. Okay, and then on this one, we want to do the natural log. You can just type ln. So the natural log of 24, and we want to divide that by 3. Okay, so the natural log of 24 divided by 3, approximately 1.06. So far, so good? All right, now F is a little different. Okay, it's not an exponential. It starts as a log. So it's starting as a natural log, and the X is in the argument of the log, meaning it's part of what we're taking the log of. So instead of going from exponential to log, we're going to go in reverse. We're going to go from log to exponential. So this is a base E. Since you see ln, we know it's a base E. And then the exponent would be that decimal negative, oh, that's not 0.0, that's 0 point. So negative 0.5003 equals 3x. And then to get rid of the 3, I divide. So I'm just going to plug into the calculator e to this power divided by 3. So I just type in e to the power of negative 0.5003. divided by 3. So it's approximately 0.202. And again, if your answer choices aren't written as decimals, type them in and see which one matches. Okay, we'll go ahead and just go down below that while it's showing on the screen here. We're going to rewrite this from log. Actually, this one's already isolated x, hasn't it? It's solved for x. We literally just have to type that in. So I'm just going to type in log base 4 of 256. So I need my log base 4 of 256. My answer's 4. That one I literally just had to type in. So x is 4. Okay, now L, right beneath that, I will have to do a little work. The understood base, if there is no base, is a base 10. So this is 10 to this power equals x. So I'm just going to type in 10 to the power of this long decimal, 2.096910013. And that tells me approximately, so it's 124.9 repeating. Let me scroll over and we'll do H and K here. Okay, so 3 is my base, so it's a base 3 to the power of 5 equals x. So that's just 3 to the 5th power. When you type that in, you get 243. Okay, in K, my base is 2, my power is 5, and it equals 2x squared. So now I've got some extra solving to do. Now I do need to simplify. The 2 to the 5th is 32, but I got to divide that 2 over as well. So that's 32 divided by 2, so I get 16 equals x squared. And to get rid of the square, I take the square root. So I end up with 4 equals x. Scroll over here. All right, in this format, G, we're solving for the base. So it's x to the 1/2 power equals 64. You need to, excuse me, you need to remember that 1/2 power means square root. So to get rid of that square root, you would square both sides. So 64 squared is 4,096. And again, I just typed that in the calculator. All right, J, this is a 1-to-1 property. You have log base 7 of something equals log base 7 of something else. Since they're both log base 7, you can just drop that log base 7 and say, okay, 2x plus 5 must equal x minus 3. Guys, I can't just walk out. So then we get the x's to the same side and the constants to the other. So that leaves me with x equals -8. Now we do want to make sure that when we go to plug these in, that it works, meaning it's actually part of the domain. So here, if I were to check this, I deleted the box because when I go to plug in -8, if I do -8 minus 3, I get -11. Over here, if I do -8 times 2 is -16 plus, that's -11. So you might think that it works because you get -11 in both spots, but what you have to remember is you cannot take the log of a negative, okay? So it's not the fact that it came out as a negative, the x value, it's that when you plug it in, your argument is a negative, and that can't happen. So this one actually has no solution because it won't work. You'd end up trying to take the log of a negative, which you cannot do. Okay, so you do want to double check on some of those because they may be a little trickier. Okay. I'm going to stop this video here. I'll start the next video going over these and talk about ways to look at this graphically as well.